Hi, everybody. Can you all hear me? Yep, OK. Thank you for the nice introduction. I have a question you can take a second to think about, but I would like to ask who here has ever had a moment in their life where something really good happened that was totally unplanned? Yeah, so we are all here successful people in our career, and I guess you have realized at some point that success was very important in getting you where you are now. Not success, luck. Hard work is good too, but you sometimes just have to be lucky. So I'm not the only one who believes this. This is a mathematician, Harold Kuhn. He's basically a game theory father, was. He actually even wrote an academic paper on being in the right place at the right time. He's being at the right place at the right time. He started with moving furniture for Dick Bellman, who is the father of dynamic programming. And he wrote 4 pages of very dense mathematical stories on how he was very successful. So regarding my taxi, I think my taxi would also qualify as being the right place, right time. If my taxi would be a business starting now, it wouldn't be very successful because there is Uber. But my taxi was the first ride-hailing app in 2009. 5 employees, they wrote an app. Now we are over 800 employees, mostly in Hamburg, Barcelona, and Berlin, the developers centers. And we're buying all sorts of companies everywhere. Yeah. Acquisition is cheaper than expansion. And yeah, Daimler is our main, so Mercedes, and who are becoming now friends with BMW. So it's all a happy family. So I did a speaker training, and you're supposed to have black slides, so you can look at me. OK, so in an app like my taxi, there are 2 parts of the story that we always have to care about. We have the drivers and the passengers, and we have to keep both of them happy, right? So drivers have to have enough passengers to work. They are taxi drivers. It's a competitive market, especially in countries where taxi trips are expensive. And passengers, well, you're a passenger. You want everything fast, right? So as most of you have been a passenger, so who here has not used a ride-hailing app so far? Not. OK. So in 2018, a passenger really wants, when they order a taxi or a car to get them somewhere, they want to know that that car is coming, and they want that car to come when they ordered it. And they also want, if possible, to have a nice trip wherever they go. They don't want to get abused or anything in the car. They want to have the driver reading their mind. I don't want to talk to anybody now. Or the driver reading their mind. I want to talk to you now. All sorts of things. Depends, right? So what does the driver want? Well, the driver is a bit tricky. Drivers work in shift. It's really nice because they have they can choose their time when they work, maybe. But they also want those shifts to be useful, right? They want to have maximum utilization of their shifts. They don't want to wait at a corner for passengers. They want to be able to organize their trips in a way that it makes sense. They don't zigzag through the city. So if we think of our drivers the same as we think of ourselves, it's good to be at the right place at the right time. How do we get drivers at the right place at the right time? So that's why demand prediction. How do drivers do demand prediction these days? Because without you knowing it, we are all doing machine learning in our head. Every time you infer something about something you do, and then you apply it again, that is a model that you have built. You cooking at home, and you realize that your husband or your wife or something likes something or not, next time you're not going to cook that, or you're going to do more of that. That is a model. And the same thing is what the drivers are doing on the streets. They are basically applying their knowledge of their street. They are the experts, and they're using that. So you can say, yeah, if yesterday at 4 o'clock I had a lot of demand somewhere, then I will go there again, or next week at the same time. So normally in data science, after you have defined your problem, you basically try to come up with some heuristics. Like, if I were the driver and if I would be solving this problem myself, what do I do? So let's say I take the average of all the demand in an area at 4 o'clock over the last week. So that is how I think today at 4 o'clock is going to be. So you plot that, and you get, well, it kind of zigzags, but it's not really close. So now comes the part, can we do this better with machine learning? Who of you have not heard of machine learning until today? Okay, good. Well, machine learning is really old. If you go on Wikipedia, you see it's the 50s. Neural networks are old too. Actually, it turned out that my aunt did her master thesis on neural networks in 80-something. I have not read her thesis, but I'm actually quite curious. So we could try with our baseline, like we tried the baseline with one feature, it's called in machine learning, and we could also try with like many other features manually. Okay, we give this feature a coefficient, and with this other feature another coefficient, and we see how it goes, and we can do that like over and over again until we get a really good score. But the point of machine learning is that you can just let the model learn all of that. I'm not really going to explain more than that how machine learning works. I really advise you that you do the Andrew Ng course on Coursera for that. You can do all the math. It's really cool. So once you decide that you want to do machine learning for solving a problem, you can play around with a Kaggle data set. They're really nice. And usually you have several steps in solving a machine learning problem. You define the problem, you gather the data that you need for that, you train some models, you evaluate them, you analyze the errors. Errors are bad, you go back. You may be doing this a lot of times. I can recommend you the book. So this is like a highly iterative process. Being a data scientist these days is like a very hyped job, right? You're like, oh yeah, we all want to be data scientists. It's so cool, you get to train the model. But actually, training the model is like a very small part, and the rest is a lot of work. So in our model before, we said we had like one feature, so that wouldn't work very well. So let's say the next thing to do would be to add more features, right? So we can have really cheap, there's a lot of Python tools out there to extract other time features from, you have like the date, you can get the day, you can get day of the week, you can get the hour, you can get the minute, you can get all sorts of things only out of the date. You can get if it's rush hour out of the time, you can get if it's weekend or the week, or if it's a public holiday. All of these can become more features in your training set. And you can also do, based on your data, historical aggregates, like, okay, what happened last month here? What happened last week? What happened every Monday here? It's like all sorts of, did all the drivers cancel all the time when they were there? Did passengers cancel? All sorts of features that you could enrich the data set. What is really important at this step is to try to create a data set that you stick with during your experimentation. You do not want to have everything changing all the time, and you're not able to compare with what you've done before. So now comes the really rocket science about training a model. This is it. So everything is open source. You basically you import the library, and you write about 3 lines of code. And that's machine learning for like really just starting with it, right? Of course, this model has no parameters, there's no parameter tuning, it's like super simplified, and it's just going to be like the first thing you run. So this part is like all really cool, because this is going to work better than the baseline, the one number you used before. So you're going to be like, wow. But the next part is going to be the part that starts to be interesting. It's like, so how do you track errors? So you see there, I got like get RMSE, that's called root mean square error. So evaluating your model, you could go traditional. You can say, I'm evaluating my model, I use the metric mean square error. So basically, the line you see is my prediction, and the little bubbles are the real values. And if you sum up the square of all the distance between what you predicted and the real values, and you average that, that's your mean square error. And that's basically what you try to minimize when you train the model. Now, this metric is really a little bit unintuitive, because if I'm talking of a demand of 1,000 requests in an hour, then my mean square error is 3. That means I get plus minus 3 on like when I predict. But if I'm saying that my demand is 10 requests per hour, then plus minus 3 is quite a high number. So the mean square error, to be able to interpret it, you actually have to relate to the problem that you have. What is your average demand? What is your average value that you are trying to predict? Another metric that a lot of people are talking about is accuracy. So accuracy is something that, very simplified, this means like, how often are your predictions correct? But again, because we are talking about predicting continuous values, that's like called regression, then the accuracy is more or less saying that something is correct or not. Actually, you have to define what correct means for you. So it is really important at this moment in your experimentation to actually choose one metric that all your experiments that you do, you basically compare on that metric. So you try to optimize for one metric that you think, what does accuracy mean for my problem? And it's, again, you might find out at the middle of your sprint, or if you're lucky, after some sprints, unlucky, that the metric you choose is really bad. So you have to start all over again. So the next thing we did, let's say, was we had all the features we added, and now we trained a random forest regressor, and this is basically trying out with over 40 features to combine them in every combination possible and randomly choosing things, and then at some point says, okay, this is the best. The way you do machine learning, training, and testing is basically you split your data set in a part that is called training and a part that is called testing. Sometimes you also can do validation. But let's say on my train set where I train my model, I get an error of 12%. This is called the bias your algorithm has. It is not the same bias as the one from when you're discriminating against somebody. But it is the same principle. So this is something that you can improve by getting more balanced data. You can get more data that represents better what you're trying to achieve, and also maybe get more features, better features. The other metric that you have is called variance. And variance is like when you have your model and you try to predict on the test set and you get the results, and your model is performing worse than on your train set, that difference is called variance. That means that if this value is really high, that means your model is not generalizing well on new data. That means it's overfitted on the train set. So you cannot really do that. If you have this situation, you cannot deploy this in production at all, because you will be like, it's going to be totally random. You can get bad results. So the next thing one has to do at this point in machine learning would be like, because now we are looking at these numbers, they're all averages, so the next thing one has to do is say, sure, but so 2% is really good, and 12% is for my business scenario okay, but what does this mean? So you can actually do a simple thing, is you can just plot all your values. So you have basically the blue is the real value, and you have the green, the one that is actually not seen as green, is what we did like with the baseline with only one feature, and the pink is the random forest tree. As you can see, in all the situations, even the baseline and the other one are under predicting. And actually, the baseline is really not managing to predict peak times at all. That means anyway that it's a bad baseline in this situation. So, but you should always try to win against something that is good enough. And what happens here is that you see that the predictor is doing pretty well on very low demand part on the left side. So this data set is a bit skewed. The data set currently, this means that it has a lot of data points with low demand. So that's why those data points are actually dragging the whole prediction, all the predictions down. So here would mean in the next step one would have to do is go back and do some more outlier detection, data cleaning, remove some very low values which are not, it's not worth predicting for, right? So but this is like more like you look at it, you try out, you do more things, you try out. This is like this where goes the iterative step. So what do we do with that? So with that, we want to say, sure, so what is the demand in a city? And I want maybe like simple heat map. So who here has been in Hamburg before? So you know Reeperbahn, right? Right? So the red dot there is 3 a.m. in the morning, São Paulo. Everybody wants to go home. They're very drunk. These are the lucky people if they get a taxi, because the other ones are the ones that, if you've ever been at 8 in the morning on a Saturday in the center, you see all the drunk people that are struggling to get home. It's really sad. Anyway, so especially if you try to get a plane and you're like totally sober. Yeah. So let's say we want to achieve this. So far we talked about we do a model, we do the training, we do the testing, we do the predictions, and it's really nice and it performs well. We are still at the part where we are talking as if we had a data set as a Kaggle challenge. Who here has ever done a Kaggle challenge? So, you download the data set, it's very static, you have the test side of the data, and you run your model, and you can compete with other people, and you can get really good results, but you don't deploy that anywhere. And if you want to work, so at my taxi, we have the data science team on end-to-end team, so we also want to deploy our models. So the next thing that we have to do would be, okay, how do we do that? So in a microservice architecture, we have the part where we periodically train the model. The model does not have to be trained every day, every hour. You can train it once a month, once a week, depending on the problem you're solving. Then you have a microservice which loads the model. It can be in a Docker container deployed and everything nice, and it runs predictions. And basically, this one gets requests from a user-facing application, like, for example, the heat map says, I want to know what the demand is going to be at 4 in the morning, and it gets the predictions. And that would be really good if the only features we would have would be the location and the user and the time, right? But we said we have more features. We have aggregated features on past data. So the next part is it's about tricky, and whenever you buy machine learning books or you read blogs and stuff, everybody's talking about, and then you just deploy it. So this is the part where it gets like, okay, so we have to get the same features that were used in training the model, the same features are needed for the predictions. So if in my model I had a feature which said, I want to know what is the average of requests in the last week in this area at 3 o'clock, then for today to predict 3 o'clock, I need the average request in the last week in this point. And you can't run such a query on a live database in production. So this data somehow has to come in, like you either build a streaming API on top of your data warehouse that you can collect this information. And so it's a bit tricky. And a lot of people, they don't really put this into consideration, take this into account when you're like working in I would say my taxi, 800 employees, it's like 120, 130 developers. It's still a small company compared to other companies that are here. So you really need here, at this point, if you have to think of data science as a cross team. So you actually also need data engineers. It's really good if you have in your data science team people who have strong data engineering backgrounds, developers, if you can afford to have that. So there are other companies that have the data science part working completely separate from their company, and they just give the models, and the developers implement everything. So these are all the technologies that go behind working in a data science project at my taxi. This depends, of course, on the company, right? We use Kafka, we use Python, Docker, Presto, Spark, AWS. Some people have their own servers. We use Hortonworks. Other people use Cloudera. We use Airflow for scheduling data pipelines. It's open source from Airbnb. It's really cool. And the nice thing about most of the data science tools out there is that they're all on GitHub. So unless you really, really, really want to implement a model from scratch, and then you would probably go in research or like in your hobby time of data science, because you don't always have time to do that at a normal workplace, you will use existing algorithms that are like going all the way to neural networks if you want to use that. So it's not really like the rocket science comes into how do you combine things and how do you decide on, like, do I do this or do I do that? Is my experiment good enough or do I go further? Do I stop? So nobody likes to do the error analysis. Nobody likes to do testing. It's just like normal developers don't like to do unit tests. Who here likes to do unit tests? Cool. Who doesn't? I mean, okay. So it's like the space and the tab. Okay. Part. So on the closing side, I can totally recommend that every time you think you want to get into data science and you want to learn machine learning, and think about it, why do you want to do that? And how far should you take your knowledge? So how deep should you look into things? How much should you learn? So this is a really good book. It's for normal people to read. It's not mathematical or something. And what is really good, it just takes some examples out there that have been deployed on normal human beings without some of those human beings knowing that they have machine math algorithms, like analyzing and making predictions and making decisions for them. And they have been not properly analyzed and not properly done. So this is the domain of data science, which is called sloppy data science, which is a very dangerous ground at this time, because there's a lot of tools out there if you just want to do like fast data science. And a lot of people, they skip all the steps. They just like run the first experiment, and it's like, oh, it's really working. Nice. And I test on my little test data set, and they don't have proper monitoring installed to see how often their retrained model is actually predicting wrong things, or these things that have to be done all the time in order to track that you're still doing something good. So think about yourselves, like right place at the right time, and in order to enable that for other people, you have to be responsible in the code you produce and in the work you give, like the work you do. That's it. I'm under 30 minutes almost. No, I'm less. No, I'm fine. I'm done. So, yeah. Good.
Okay, and we have some questions for you now.
Oh, okay.
Ready?
Yeah.
Okay, so first question. Does predictive demand work for regulations like in Vienna, where Chamber of Commerce forces cab drivers to return to their base after every ride?
Yeah, but that doesn't have anything to do with the drivers, right? It has to do with the passengers. So the demand prediction is basically something you do for to detect where passengers are going to be. And you would have to keep that in your model, this information that drivers might systematically be further away than you would think.
Okay.
And also there's less drivers in Vienna.
Okay.
So demand prediction for now it's going to take a while to get to Vienna.
Okay, and one of the popular things today, the data protection in Europe. How does this apply to machine learning? How can you unteach a machine if someone decides their data should be removed?
Yes. So what we are currently doing is the part that we have is that we don't use the real full location. We already used approximate location. So we are starting with end of next week. We will not be allowed to have access to location that is more fine-grained than 25 meters. And that's fine. I mean, we use, basically for our experiments now, we use 1 kilometer. So, but what we would have to do if we have figured out that a passenger has said that they want to be removed from all their transactions be removed from our data, then we would have to retrain the model without that passenger.
Okay. Is it possible?
Yes.
Okay, perfect. And for the last question, Python or Python?
Python. Sorry. R is also cool, but Python is...
Okay.
Yeah.
Thank you once again.
You're welcome.